Okay, thank you so much. Okay, so good evening to all of you, and we are here with a very fresh chapter, yet a little oldie. So we are here with KTG and Thermodynamics Part 2. So in this part, we are going to discuss about KTG. KTG, anyone can guess what is the full form of it? Any one of you? Okay, no worries. I will tell you about that. Yeah, very good, Ganesh. So as Ganesh has answered, the same way I am going to answer. The KTG means kinetic theory of gases. Kinetic theory, kinetics. Do you understand? Kinematics, kinetics, which means in this theory, most of the part deal about the motion, momentum transfer, force applied, all of these things. So that is the theory that we have developed. Okay, to understand the motion of a atom or molecule inside a solid, liquid, or gas. Okay. Now, firstly, what we are going to learn, what is the learning objective of this chapter? So, first of all, we will study about behavior of gases and their kinetics, their motions, and all. Then we will understand about the equipartition law of energy, that how the energy is distributed inside an atom. My voice is not clear. This is because of my health is not good, so that is why the voice is breaking. Just a second. Now it is clear. So I think now it's clear to you. Okay. So in this chapter, we are going to learn about the behavior of gas and their kinetics. And then we are going to learn about the equipartition law of energy and energy of gases. Equipartition law of energy suggests us that how we distribute the energies to the atom, or how energy is distributed in atom among cells. Okay. So these are the two topics, although there are multiple topics in that we would like to cover in this chapter. So firstly, behavior of gas and their kinetics. Now, in this learning objective is the postulate of kinetic theory of gases. This is very important and very crucial information. And you can expect at least two questions from this chapter in your JEE main and NEET also. Okay. So this is very crucial chapter and important also. Then Maxwell speed distribution law. This is not very important and none of for your use. We will calculate the pressure applied by a gas, or this is also termed as pressure calculation. And then we're going to learn about the kinetic interpretation of temperature. Okay. Now firstly we will discuss something about the equation of state of a perfect gas. Okay. So we all know that in your chemistry also you have learned various laws in the ideal gas chapter. Okay. So there are various gaseous laws, which is firstly I will discuss about. The first one is Boyle's law. So what does Boyle's law says? Boyle's law says that if number of molecules and temperature of a gas is fixed, then pressure will directly proportional to 1 by volume, or pressure inversely proportional to volume, you can also say that, which means increasing pressure you will see a decrease in volume. Okay, similarly you can write this as PV is directly proportional to something like say constant K. Okay, so we can write for two process P1 V1 is equals to P2. If a gas is going to change its pressure from P1 to P2 and volume V1 to V2 at same temperature and same number of molecules, so this law will be valid for that. Now, second law, if I talk about second law is the Charles law. Okay, so same thing. If number of molecules or atoms and this time we would fix the volume, and volume of the gas is fixed, then according to Charles law, pressure is directly proportional to temperature. So for two process, we will have P1 upon P2 is equals to T1 upon T2. Or you can say it in another word, P1 upon T1 equals to P2 upon T2, which means at fixed volume, increase in pressure will result in increase in temperature. Okay. Now, these are two laws, Boyle's law and Charles law. One of the famous law is also there, is the Avogadro's hypothesis. Avogadro hypothesis says that if pressure, volume, and temperature of a gas is fixed, then for a specific volume, the number of molecules or atom is same for every gas. Okay. Or in other word, you can write it as Avogadro's hypothesis. At same pressure, temperature, and volume, any two gas will result in same number of molecules. Okay. So at that particular volume is 22.4 liter. That temperature is 273 sorry, T is equals to 25 or 27 degrees Celsius and pressure is 1 atmospheric. This condition is for specifically STP, standard temperature and pressure. So at STP, every gas possesses the same number of molecules and that is equals to 6.023 10 raised to the power 23 molecules or atom. Okay. So suppose you have take hydrogen gas and nitrogen gas at same volume. 22 point liter you have taken for hydrogen and 22.4 liter you have taken for nitrogen. So the number of molecules in both the gases will be same, which is equals to 6.023 10 raised to the power 23, and which is equals to 1 mole of gas. Okay, good. Number of moles, how you can calculate? It is mass divided by molecular mass or molecular weight. Okay, but this number you have to remember, this is the Avogadro's number. This same laws you have seen in your chemistry also, chemistry subject. Okay, and these are all going to help us right now. Now if I combined all these law, by combining all these laws, what do we left? Firstly, we will have Charles law, sorry, Boyle's law. P is directly proportional to 1 by V, or PV is directly proportional to some constant. Then we have another law which is P is directly proportional to T. Okay, got it? Now, if you combine this, you will have PV is directly proportional to T. And if you remove this constant, you will have PV is equals to mu R T. This is the ideal gas equation. And here R is the universal gas constant, which has a value of 8.31. Mu is the number of moles. Okay. P is pressure, V is volume, and T is the temperature. So this is the ideal gas equation that we have. Okay. Now, so any kind of doubt in the previous laws and Avogadro's hypothesis? If you have any kind of doubt at any point of time, you can ask. Okay. Now, kinetic theory ke postulates. This is very important and try to remember all of this. So postulate of kinetic theory of gases. The first postulate is that all gases are made up of molecules moving randomly in all direction. So this is very simple postulate. You can see here in the emanation, these are, you can consider the molecules of any gas. Okay. So these molecules are moving randomly in each and every direction. No one can define the exact direction of their movement. So that is why the first postulate suggests that all the gases are made up of molecules which is moving randomly in all directions. Okay. So this is the first postulate. You can take the screenshot of these or you can note it down in your notebook. Noting down these points on your notebook, that will help you a lot. Okay. And it is better than taking a screenshot. Now, postulate of kinetic theory, my second postulate is that the size of a molecule is much smaller than the average separation between the molecules. What it is trying to say that this is the size of molecules, let's say diameter of this particular molecule. And this is the separation between these two molecules. So the postulate is saying that the size of molecule is much smaller than the average separation between the molecules, which is, we can say this D, capital D, is very, very greater than this small d. So we can say that the path of this particular molecule will not be disturbed by this molecule, and this molecule. So it can move freely inside the gas. And if any particular body is free, so we can apply the Newton laws of motion there. So Newton laws of motion is applicable here. Okay. So the molecule exert no force on each other and on the walls of the container except during collision. So without collision, if they make a collision, then they can exert a force. Otherwise, they are not exerting force because there is a large separation between them. Okay. Now, this is an important postulate. All collisions between two molecules or between a molecule and a wall is perfectly elastic, which means energy and momentum both are conserved in that case. And these collision take very less time. Okay, so this is very microsecond time it will take to make a collision, and that is to be a perfectly elastic collision. Okay, so all collision between two molecules or between a molecule and wall, if they are striking the wall also, then also they are making a perfectly elastic collision, or you can say only elastic collision, in which energy and momentum both are conserved. Got it? So this this is the example of elastic collision. This is moving with velocity v downside. When it is strike, it just changes its direction without changing its speed. So that is why we can say here the momentum is conserved and the collision is elastic. No. So that is why these molecules obey the Newton laws of motion, because in that chapter we study collision. Okay. Now, when a gas is left for sufficient time, it comes to a steady state. Okay. So the density and distribution of molecules with different velocities are independent of position, direction, and time. For example, these are the molecules at different speed. Okay. So these are the number of particles versus speed of the particles. So if you will see, for 1 meter per second, there are two molecules. For 2 meter per second, there are three molecules. For 3 meter per second, there are three molecules, and for 4 meter per second, there are three molecules. Okay. So when a gas is left for sufficient time, suppose you have taken a gas in a container and you left it for, let's say, for 2 hours or 3 hours. So what will happen? It comes to a steady state because the molecules make collision, they strike with each other. And after some time, the enough momentum has been transferred, so they will come to a steady state. Okay. You can see here, in the end, all the molecules are in rest. Okay. You can see here. Okay. Now, this is all clear to you? The postulate of kinetic theory of gas. I will discuss it once again because this is very important. So the first postulate is all gases are made up of molecules moving randomly in all direction. So gases are made up of molecules which moves in random direction. First thing is that. Now, if a molecule is moving, what is the size of molecule and what is the separation between them? Does they collide with each other? So these are the question to write the this kinetic theory. Now we know that gas is moving with the gas is made up of molecules which are free to move in random direction. Now, if they are free to move, does they collide? Yes, they of course they are collide. So what is the type of that collision? That collision should be perfectly elastic or elastic collision. Okay. Now, What is the size of that molecules and what is the separation between any two molecules? So size of the molecule is very less, and it is very less in comparison to the distance between them. Okay. So net force exerts on a molecule of gas is zero. That is why gas expands freely and acquire the volume in which you throw the gas. Okay. Suppose you have a room and you have only 1 kg of gas. You put that in a room of whatever the dimension is, the gas will be all there. Okay. Because of the random motion of the molecules, and there is no interacting forces on a particular molecule. So this is D, this is capital D. So D here is very, very greater than small d. Now the molecule exert no force on each other and on the walls also, the container, except during collision. So when they collide, then only they exert force on each other. And let me tell you a story. There are interatomic forces in between these molecules or atoms. Interatomic forces. So the property of this interatomic force is that when they are separated by a very small distance, they will attract each other. But when this distance is decreasing, and let's say there is a very, very small distance in between them, okay, with a unit of 1 angstrom or let's say zero point 0.1 angstrom, when they are at zero point 0.1 angstrom distance away, the same atomic forces will now become repulsive. Okay, so they repels each other for that moment. So if you want to take away a particular molecule from the other molecule, it will attract it. But when you will say, okay, you don't want to let it go, so I will give it to you. And when you want to give it to the molecule and squeeze it, then it will repel it. So this is the amazing property shows by these gaseous molecules. Okay. And this is the true beauty of this interatomic forces. Got it? Now, the next postulate is all collision between two molecules or between a molecule and wall is elastic, which means in elastic collision, the same momentum will be conserved and the energy will be conserved. Got it? Newton's law is obviously followed by them. And this, then when a gas is left for sufficient time, it comes to a steady state. So the density and distribution of molecules with different velocities are independent of position, direction, and time. Okay. So the density and distribution, suppose most of the molecule, 5 number of molecules or 6 number of molecules moving with 6 meter per second. One molecule is moving with 1 meter per second. And why is so? Because they move in random direction with different speeds. Motion is so random. So we can say that the density and the distribution of molecules with different velocities and are independent of position, direction, and time. Because they are moving randomly, so they are independent of this position, direction, and time. Okay. So these are the postulate. The first postulate is that the molecules move in random direction. Second postulate, the size of the molecule is very less comparison to the separation between any two molecules. Third postulate, when they collide with each other or with the wall, that collision is to be perfectly elastic collision, which means momentum and energy will be conserved there. Got it? And this one, when a gas is left for sufficient time, it comes to a steady state, and the group of molecules moving with different velocities and the density of that particular group is independent of the position, direction, and time. So these are the simple postulates. Okay. I hope you got it. Now, if we move next, now with the help of this kinetic theory of gases, we are able to calculate the pressure exerted by the gaseous molecules on a wall and the kinetic interpretation of the temperature. It is only helpful because of the kinetic theory of gases. Okay, because if kinetic theory of gases does not tell us कि the molecules will collide with each other or with the wall with elastic collision, then how would I will calculate the pressure? You will see that we will take that postulate from the kinetic theory that the collision between the molecules and the wall is elastic. Now, some definition. First of all, root means squared speed. You have heard about this term. Root mean square. First of all, what you have to teach, the RMS value is set for the values of a square root of arithmetic mean of square of the values. Okay, this one. You have the velocity, you have square it. Then all the squares of the velocity, you take the arithmetic mean and then you square root it. So this will become root. Firstly, this root has come, root, mean, and then square. Okay, so that is why this velocity is termed as root mean square velocity or RMS speed. Translational kinetic energy of a gas. The total translational kinetic energy of all the molecules of gas will be equal to the summation of all the kinetic energy of different molecules. Okay. Suppose in a gas we have 100 molecules. Okay. So the total kinetic energy will become 100 times kinetic energy of any one molecules. Okay. Now this summation of all the kinetic energy possessed by single molecules. So 1 by 2 mv square. And then we sum it off. Now calculation of the pressure of an ideal gas. So I will give you an idea about that so that you will understand that what is happening inside it. So for that we will consider a small volume, cubical one, of a gas. Okay, so this is the container that we have. This direction is x-axis, this is y-axis, and this is z-axis. Okay, this you can consider a small room. And here we have a molecule, okay, which has a velocity, let's say, which has a velocity Vx I cap plus Vy j cap plus Vz k cap. So this is the velocity of this particular molecule or atom. Okay. Now, this is only we are considering this wall, the wall which is present on XYZ plane or in the X direction. Okay. So what we are considering that this molecule strike this wall and then move away. So if I consider this is the wall and this molecule is coming in this random direction, then it make the collision and move away in the opposite direction to that. Got it? This angle and this angle must be same because this collision is elastic. So if you see in this particular collision, only the direction has changed. Huh? But for which axis? The x-axis. Because it is moving in this direction, the x direction is x coordinate is changing or the velocity of x-axis is changing. And then after striking on this wall, it move in this opposite direction. So we can say that velocity in x direction has changes, not in terms of magnitude, but in terms of direction. So If you calculate the momentum transfer, let me change the color. So if it is striking, the momentum will be conserved because the velocity has changed. So momentum will be convert. So momentum transfer, momentum change or transferred by a molecule is given by delta P is equals to delta P for 1. Initially, it is moving with only x direction momentum has been changed because only x direction vector has been changed. mvx minus, now it is moving in this way. So minus vx I cap plus vy j cap plus vz k cap. We are only considering the x-axis. Okay. So it will become minus mvx. The momentum transfer will here be 2mvx. So this is the momentum transfer to the wall. Now, what is the momentum transfer of molecule? So you apply the minus sign. That will be the change in the momentum of this particular molecule. Okay. Now, you know that this particular molecule here, this particular molecule in delta t times, what is the distance covered by it? So in delta t time, distance covered is equals to Vx into delta t. Okay, because V is equals to S by T. So from S is equals to V into T. V we have taken X6, so it will be Vx into delta T. What is the area of this particular wall? It is A. So the volume covered, the volume of, or the volume is equals to A into Vx into delta T. So this much of the volume we have considering the particular volume of in which these all the molecules which is moving in x direction we have considered in the volume. Okay, because this is not a single molecule which is moving in the direction of this x-axis. So here is the that wall, and these are the number of molecules which is moving with in x direction. Now, how much is the volume of these molecules? So it will be A into Vx into delta T. Why we have taken A? Because this is the area of cross section of this plane in which this molecule are striking. Okay. So this area multiply by this distance or velocity into delta T. So it will give you the volume. Now this much of volume is moving towards this wall with a speed Vx. Okay. Now in delta t time, what will happen when they are colliding with the wall? When they are colliding, suppose in this, just imagine in this your mind, as they are moving towards the wall, not at the same time complete volume or complete number of atoms has been striking the wall at a single time. No. So if the change in momentum, which is 2 mvx, has taken place in delta t time, so what is happening? Suppose this is the molecule, this is the molecule, this is the molecule. So this molecule has strike, now it is moving in this way. This molecule has strike and moving in this way. This molecule has strike and moving in this way. This is the molecule which is coming in this way. This is the molecule which is coming in this way. So what is happening? Half, averagely, half of the number of molecules are striking the wall and moving away from the wall. Okay. So half number of the molecules is striking the wall and half number of molecule have shifted from their self from the wall because they have just strike the wall and moving away. So in that particular delta t times, when this momentum change has been happened, half of the number of molecules has been transferred to the wall and half number of the molecules are moving away from the wall because they have make the collision already. Okay. So this will be look like this. This is the molecule. It has made the collision change in momentum. It is 2 mvx. It has done and now it is moving in this direction. So for delta t time, this process happen in delta t times. So in delta t times, this molecule is coming towards the wall and this molecule is going away from the wall. Now this is not happening for only this molecule. There are number of molecule in this. So we can say that half of the molecule is going towards the wall and half of the molecule is going away from the wall. Got it? Everyone? Any kind of doubt? Okay. So if I calculate the number of molecule which cause the change in momentum is equals to 1 by 2 times this much is the volume of that particular molecule set and let's say the number of molecule is n, so we can say that 1 by 2 times n into a into vx into delta t. Why we have taken half? Because I have already discussed just before this topic. This molecule is coming towards the wall, striking and moving away from the wall. So in delta t times, half of the molecule is going towards the wall and half of the molecule is moving away from the wall. So we can say that only half number of the molecules striking on the wall or change the momentum of that particular wall. Now we can say that force exerted by these molecules, force exerted by these molecules F is equals to what? Delta P by delta T. So delta P we have calculated 2m into Vx and this is the number of molecule which are causing this change. So 1 by 2 times m into n a Vx delta T into 2m 2m Vx divided by, and it is not m, it is n. 1 by 2 times NaVx delta t na 1 by 2 times NaVx delta t into 2m into Vx divided by delta t. So this will cancel out. Now what should be the pressure value? Pressure change. Pressure is nothing but force upon area. So this area will also cancel out for pressure. So pressure exerted here is 1 by 2 times, sorry, 2 and 2 will also cancel out. So it will become N M Vx into Vx will become Vx square. Okay. Now, this is not only happen in the x direction. Same way we can consider it for Vy and for Vz also. Okay. So averagely we will take the average velocity there. So average velocity will become V bar square will become 1 by 3 times of Vx square plus Vy square plus Vz square. Okay. And this is nothing but this average velocity. So we can say this pressure is equals to 1 by 3 times Nm V bar ka square. Okay. So this is for the idea of your. Now we will discuss it. Take the screenshot and all if you want to take it. Now, the same way we have considered this. The length of this is L. An ideal gas is filled into this. This is the particular molecule having velocity in these three directions. Now, pressure by the gas on wall is F upon L square. L square is the area of this particular wall. We know that force is nothing but dp by dt. dp is delta p by delta t. So change in momentum of one particle in one collision is 2 mvx. How it has come, I have already discussed it with you. So the time between two collision with wall is this. Let's see it again. 1, 2. Okay. So this is the x-axis now. So delta t will be the distance covered by it, which is 2L divided by Vx. Now, so force is delta P by delta T. So this is mv square upon L. Total force by all the molecule will be F total m by L Vx1, all the molecules which is moving in x direction. So I have supposed that n molecules are moving in x direction. Now the total force by the molecule in delta T time is m by L sigma of Vx square. Now, due to symmetry that I have discussed, it is Vx square is equals to Vy square equals to Vz square. And this all assumptions we are making because of the kinetic theory of gases. Now, for velocity of any particular particle, V1 square is, or you can say V1 is nothing but square root of Vx1 square, Vy1 square, Vz1 square. From where, if you take the squares, this expression will you see. Okay. Now, for V3, and there are number of particles. So summation of all these velocities, summation of velocity in x direction, summation of velocity in y direction, and summation of velocity in z direction. Okay. So we can say that this is because Vx square is same as Vy square and it is same as Vz square. So it will become 3 sigma Vx square. So you can replace it by this summation of Vx square is nothing but 1 by 3 times of V square. Now, the total force in delta time will become 1 by 3 m by L V square. So now multiplying and dividing the pressure by number of particles. So it will come out as this expression you have to keep in your mind, which is P is equals to 1 by 3 capital M by capital V, where capital M is the total mass of the gas and V is the volume of gas. V square by capital N. Okay. And this MYB is nothing but the what? MYV is density, mass upon volume. So this will become V square upon N. Got it? And this V square upon N is nothing but V RMS. Root means square speed. Now, any kind of doubt, guys, you can ask right now. Then we will start this kinetic theory of kinetic interpretation of temperature. And we will see then what the temperature actually is. And I have already told you, if you have attended the previous lecture in thermodynamics, that temperature is nothing but the kinetic energy possessed by a particular molecule inside a gas. Okay. So this is it. You have to, any kind of doubt you can ask right now. Okay. Now, kinetic interpretation of temperature. Now, according to kinetic theory of gases, this is the pressure 1 by 3 times rho, which is density Vrms square. Okay. Now we know that rho is nothing but mass upon volume. So from equation 1, you can write PV is equals to 1 by 3 mass into Vrms square. You have put the value in this. I'm doing it here. Make you understand P is equals to 1 by 3 M upon V Vrms square. This V will go this side, so it will become PV 1 by 3 MVRMS square. Okay. Now, from ideal gas equation, what do we know? PV is equals to mu RT. We know na? PV is equals to RT for 1 mole. Now, comparison, if you do, it will become RT is equals to 1 by 3 M into VRMS square. Now, temperature is equals to 1 by 3 M upon R Vrms square. This M upon R is nothing but a constant we can consider for a gas. So here we can say that root mean square speed of a particular molecule of a gas is directly proportional to the temperature. So the temperature of a gas is due to its motion, Vrms, and vibration only. So any particular body which is hot and cold is possessing that hotness or coldness because of the speed of that particular molecule, and that we measure at the at temperature. Okay, so that thing is temperature. So as Vrms increase, temperature will increase. As Vrms decrease, the temperature will increase. Okay. Now translational kinetic energy of gas. So total translational kinetic energy means when we shift the molecule without rotating it. Okay. So rotation here is not given, only the shift is taken. So that is why this kinetic energy is termed as translational kinetic energy, and which is given by half mv square. So this energy is termed as translational kinetic energy. Now, the total translational kinetic energy of all the molecules of the gas will be equal to the summation of kinetic energy of each and every molecule. Okay. Now, this is the expression kinetic energy summation of all the kinetic energy of all the molecules. So it is 1 by 2 mv square. Now, if you divide this expression and multiply with n, which is the number of molecules, so this v square by n will become Vrms. Vrms it will become. So this is kinetic energy 1 by 2 times capital M into Vrms square. Now the kinetic energy, average kinetic energy of a molecule is kinetic energy. If you divide it by number of molecules, this will become the average kinetic energy, and which is given by 1 by 2 times capital M over capital N Vrms square. We are dividing this expression. Okay. This Mn here for one molecule, the mass is small m, and there are number of molecule is n. So if you multiply it, you will get to know capital M, which is the total mass of gas. Okay. Suppose if you have one orange, weight, let's say 100 gram, and similar type of oranges that you have is 100 oranges. So what is the total weight of that oranges? So you will multiply this number of orange, multiply the weight of one orange. Okay. Similar way, the weight of one molecule is small m, and if we multiply it with capital M, which is the number of molecules, so it will give you the total mass of the molecule. Oh, sorry, total mass of the gas. So 1 by 2 capital M Vrms square. Now for the average value of kinetic energy, what we will do? We will do K1 plus K2 plus K3 up to Kn divided by N, which is the number of molecules. And this Ke is the molecular energy of all the molecules, which is K1 plus K2 plus K3 plus Kn. So if you divide this energy, kinetic energy, with the number of molecules, then you will have the average kinetic energy of the molecule. So kinetic energy divided by N is 1 by 2 times mass, total mass, divided by number of molecules, Vrms square. Now, kinetic energy, this will become again small m into capital N is capital M. So small m will become capital M over capital N. So this will become 1 by 2 times m of Vrms square. Now, again, if you will see here, this will become capital M Vrms square. Same as this. So this energy is also, you can say, is the average kinetic energy of a molecule. Okay. Now multiplying this expression, because we are trying to relate it with the temperature term. Okay. So this will become kinetic energy is equals to 3 by 2 times 1 by 3 m Vrms square. We have multiplied this expression by 3 times that we have previously called. It is 1 by 2 times capital M Vrms square. So if we divide this expression by 3 and multiply it by 3, so we will take that divided by 3 with this. So this is nothing but pressure. Okay, 1 by 3 m Vrms square. So pressure we know, it is 1 by 3 capital M by V volume Vrms square. So we can put that value here. So PV is equals to 1 by 3 times of M Vrms square. So kinetic energy will become 3 by 2 times PV because it is same as this. Okay. Now, although on the other side, for ideal gas, PV is equals to mu RT, the equation that we have seen initially in this lecture. So for 1 mole, PV is equals to RT. For 1 molecule of gas, we can say that PV is equals to R upon Na. Na is the Avogadro number. Okay. And this R upon Na is nothing but Kb, which is Boltzmann constant. So you have to remember this. Okay. This R upon Na is equals to Kb. Okay. So PV will become Kb into T. Now, if you compare this equation 3 with equation 2, so kinetic energy of a particular molecule will become 3 by 2 times Kb into T. So you can see here the temperature is nothing but the kinetic energy, average kinetic energy possessed by a molecule. Now, based on that, root mean square speed. So it is called the square root of mean square speed. Firstly, you have the speed, you square it, then you take the mean of it, and then you square this, square root. Okay. This is called the Vrms. Okay. So Vrms, we know that 1 by 3 mv Vrms square. So from this data, you can calculate this Vrms is nothing but square root of 3 PV by m. And if you want to replace this PV with the help of temperature, you can also do this. For ideal gas, 1 mole. So RMS will become here, PV is equals to R by Na into T. Now we replace it. So Vrms will become 3 kBT over M. So this you have to remember only, not this expression. This is not so much of worth. Only this expression you have to remember. So Vrms is the square root of 3 kBt by m. And you put the value of kb here, which is r upon na. Kb is equals to r upon na you can put. So Vrms will become square root of 3RT Na into m. Na into m will become total mass of the gas or the molecular weight of the gas, because Na is the number of molecules at in 1 mole, and which is nothing but the molecular weight. So Vrms here is the square root of 3RT by capital M, where capital M naught is the molecular weight of the gas. The same thing is doing there. 3RT upon M naught. Okay. Now there are two velocities more, Vmp and V mean. If you compare these velocities, V mean is the average velocity of the particular molecule. Vmp is the most probable velocity, by which this is the most probable velocity that a molecule can have. Okay. The more chances is to acquire this Vmp. So this is the relation between them. Vrms is the highest velocity, then V mean, and then V. So expression for most probable speed is 2RT by m naught. Expression for mean is 8RT by pi m naught. And for Vrms it is 3RT by m naught. So I will write separately here V mean is equals to 8RT upon pi m naught. And Vmp, MP means most probable. It is equals to square root of 2 capital RT upon m. Okay, got it? If you multiply this RMS with 2 and divided by 2, so Vrms is equals to square root of 3 into 2, or you square root of the most probable. If in this expression, if you multiply it with 3 and divide by 3, so it will become 2 by 3, 3RT upon m naught. 3RT upon m naught is nothing but the Vrms. So you can write V most probable is square root of 2 by 3 times V of RMS. This expression also you can note down. Okay, so this is it. These laws I have already discussed, so no need to discuss here. So this is it from my side for today. If you have any kind of doubt, you can ask. Otherwise, the lecture is been over. So thank you so much for being attentive. Any kind of doubt, you can ask. Otherwise, thank you so much. Have a good day.